So, okay, there is the Directory 2+7 manuals, tutorial manual. In general, no matter if you are interested in quantitative phasor analysis or any other application, remember the Topaz license you have got is working till end of the year, so you have plenty of time, if you care, to look at these tutorials. They are all step by step, really dedicated for the beginners. So there are general profile analysis techniques, for example, individual line fitting, whole powder pattern fitting, indexing for structure determination is an important part of it. Whole powder pattern decomposition, Pauli method or Lebye method. And then, of course, the structure determination part, which Robert showed. Plenty of examples. I mean, pick some if you want to do it at home. You should be able to do that if you simply follow this approach here. The quantitative phase analysis part, which I at least want to demonstrate in a couple of minutes to you, is also all found here. And the required, let me just close this, the required data are all found in the directory tutorial. Here's a different profile fitting methods and other associated applications. There would be the quantitative phase analysis directory. There is pretty much all methods covered which are implemented in Topaz. I only discussed 2 or 3 today, like the Rietveld method, internal standard method, and points. There are others which you may want to look at. And whenever possible, I was using data from the Rietveld round robins. So these data are still available also on the internet if you go to the Commission of Pauli Diffraction webpage. And I like them just for educational reasons. These data are fine. There is no real issues with them. And to as a starter, to become familiar with the software and also to find out how good you can solve the task, it's just perfect. It's better than any data from anyone, and you just try to play with it and you have no ideas what's maybe wrong about the data. So this was a preface. Do you remember what I said right at the end of my last presentation? What is part of every good school?
Amen.
Yeah. I love exams, in particular if I'm not taking them.
Don't.
So, this is a powder pattern. I zoomed in a little bit, the upper peak intensities are cut off. Can you tell me what the background is?
I'm home.
What's it? Okay, I give you 3 different. Three different functions. It's all a little bit, extremes. You may like or hate some more than the others. So I'm going to ask you to raise your hands later and to tell me which one you prefer, which is closest to the one you would choose. That's my proposal number 1. That's my proposal number 2, the typical polynomial. And that's my proposal number 3. And now please raise your hands. And I really want you to raise your hands. We do this as long as everybody raises their hands, and if it's for the rest of the day. So who prefers this background the most? Surprisingly high number. Interesting. Who likes this one the most? The vast majority, as always. And this one here? Yeah, you see, we have still the same educational issues as 30 years ago. So, shall I tell you? Why?
Because that there is the only like that. It's not because the other provided to your plane for provide or that.
Yeah, they are used though, but inappropriately. But what alerts us that it cannot be, for example, I mean, this here is obviously not correct, although it is often being used in Face ID. Some software is using this sort of background for Face ID. In Face ID, it doesn't matter if you cut off intensities from your peak tails, because the important information is, first of all, the peak position and the relative intensity, but the error by such a background subtraction would be small. It would not really affect the Face ID unless you subtract, maybe by mistake, a very tiny peaks. So this could happen. This is used. There's some analytical techniques where this is being used, but it is definitely incorrect. No way. So why do always most people select this function? Because of course it's curved. I mean, this here is. I mean, background is never horizontal. I mean, it is never horizontal or constant. Many people assume that it is fair to use such a background because they assume that this here is actually the baseline of the background, or here. This is why they put the data points down here, because they assume that this is the background level, the baseline level. We've seen that also yesterday clearly in the exercise with Face ID. So why do I know that this is the correct background? I think you guys, you got it. That's a calculated pattern, and I added 100 counts background. So this therefore is the true background. So why do we fail so often in practice when it comes to background determination? Why would even the software do that? Now, yeah, we have peak tails, right? And the more peak tails we have, the more peaks we have. The overlap of the peak tails seems to raise the background at high angles, but it does not. What happens is, if you subtract now such a background, you delete a lot of intensity, or in the case of the refinement, you consider a large portion of the peak tails at higher angles as background. In a structural refinement, for example, the consequence would be significantly higher temperature factors, simply because the higher angle intensity has been reduced. So such a background here is unrealistic. It is just for the purpose of this little exam, but it would have been the correct one. And all the intensities you can see here below, below the peaks and the red line. This is all peak intensity. This is all the intensity in your peak tails, and you should never ever touch them. But the problem is, how do you avoid that in practice? It's extremely difficult. Often you cannot. Fortunately, in many applications, it's not so important if you touch it. So also indexing, for example, would come in mind, apart from the fact that you would use lower angle peaks anyway, but indexing is also not intensity critical. But structure determination is. Quantitative phase analysis obviously as well. Okay. So what about this one here? I showed that before. Any ideas? I mean, if you cannot discriminate whatever we call background right now, we should also have the discussion, what is background actually? What is in the background? It's partly mentioned here already. There is equally no hope to do an accurate background for a pattern like that. And it is certainly not horizontal or constant as in the previous example. So what could we do? Any ideas? What could we do to maybe get a better idea of what the background, or rather the components of the background are. Remember what background components you could have. For example, air scatter, essentially the instrument background. Most of the instrument background is air scatter. You may have scatter from some components if your instrument. Normally, in our experience, that is not dominating. So most of the scatter you see is air scattering, and it is most prominent at very low angles to theta. So you will, as you come close to the primary beam, see more and more air scatter. So the background, or what seems to be background, is always getting high at lowest angles to theta. So we have air scatter, maybe instrument components. What else? Yes, sample fluorescence. No? In this particular case, there is no fluorescence, but it can contribute a lot. Now, fortunately, if your slit settings of your instruments are right, fluorescence is equally distributed in all directions. So normally it will only raise your background by a constant value. So that is something which could be dealt with. Interestingly, if you find a way how to determine the background intensity in the case of fluorescence, like if you have, for example, iron fluorescence, you could even determine the iron content in your sample from the background if you wanted to. I don't know why you wanted to, but you could. Amorphous faces, right? One or more. Yeah. Can you tell me, these diffract or scattering bands here, where's my mouse? This is obviously an amorphous phase. It could be the sample holder. Sometimes people use two large divergent slits, and at lower angles they illuminate the sample holder. So if it is plastic, you will see such a amorphous band. And here's something like the second order. Can you tell this is one or two amorphous phases? Difficult. No? Well, in this particular case, it's one. But if it was two, it's very hard to tell. The peak overlap would be much too hard. No? So essentially, the task here in this particular case would be, can I discriminate between what is instrument background, air scatter or scattering from components, something which should be constant from measurement to measurement, always the same. There's no reason why the instrument scatter should change from measurement to measurement. It could be amorphous phase, maybe two, but yeah, in the peak tails. So sometimes, not always, sometimes, and in particular, if you do more systematic work on a particular problem, you can work this out. And this is something I would like to show you in the context of quantitative phase analysis. So I would say, if you're only dealing with a singular pattern, then you have a problem. But you can, for example, have, for whatever reasons, the possibility, or you're lucky enough to have, no, that's not what I wanted, the amorphous phase pure. If you have the amorphous phase pure, you have already done a very important step, because that now would allow you very easily to model the instrument, the intensity distribution of the amorphous phase. And if I have the intensity distribution of the amorphous phase, then I have a possibility also to refine that in subsequent refinement. Still, I have the background of the instrument here. Now, the determination of the instrument background could be done with a standard reference material. This here is corundum. It should be perfectly crystalline as far as it's possible, like LAB6, silicon, this type of standards from NIST. And if you have a measurement like this one, and this here already works, you have enough data points, also at high angles to theta, where you could say, yeah, that's definitely baseline here. That's baseline here. There is no peak overlap because there is no peaks. With silicon or LAB6, it would be even easier, even better. We just have to make sure that there is A, no sample fluorescence, and that there's B, no amorphous material in your sample. And by the way, if we're talking about a perfectly crystalline material, 100% crystallinity, does such a material exist? So it has been shown by the guys at NIST that even in what is assumed to be a perfectly crystalline sample, you have the surface layer, the non-diffracting surface layer around each particle, around each crystallite, and reaction products or absorbance or whatnot in a finely divided material account for 1 to 3% of amorphous material. So there is no such thing like 100% crystalline material. Just the surface of your crystallites in the powder with the crystallite size we need contributes 1 to 3% amorphous material. Yeah. Jim Klein, NIST SRM 676. This is a very nice work from 2011. I can provide you with a reference if you want to. Yeah, I think it's nice to know. It will not drastically change our analysis, but I think it's interesting to know. So, what can I do here? I can get a very good idea of what my instrument background is, if I measure the standard, and if the instrument is remaining unchanged between my measurements, then I can use that as a constraint in all my other subsequent measurements. Yes, please.
I got the separating like repeatedly. I think that the measure the empty rather than the standard run model.
Yeah, fair question. This is reflection data, but the approach would be exactly the same. I mean, you also in the case of a capillary, I mean, on Wednesday, tomorrow, we will be talking about PDF extensively, and I assume that Max will discuss the background in PDF analysis when you generate the PDF. The approach is exactly the same. Also, you have the component instrument scatter, but you have now a true second phase, which is unfortunately not part of your sample. So you couldn't quantify it, but to the fact that you have the sample inside of the capillary for the beam, it is one and the same sample. So you have the contribution of your capillary, and that's exactly the same thing at the end of the day as here in the reflection case. In the reflection case, I can do quantitative analysis. In the capillary case, it doesn't make sense. Yeah, please.
Would it be possible to just measure area scattered? So you just measure without.
Yeah.
Right.
You could. You need to keep in mind, and this is something you always want to check out. Often, because of slit settings or of sample size, you are also eliminating the sample holder. So the sample holder could add a contribution. This is something you always want to avoid if you can. Avoid it at all costs, or you get problems which are not easily fixed. And the second is, if you take the sample holder out, and this is obviously true for reflection instruments, you will illuminate the instrument much harder. And I mean here, if there's any instrument parts made out of iron, you can imagine what happens. So yeah, you could do that, but if you do that, try to do it a little bit systematically. Try different things without sample holder, and make sure that the measurements, the data for the background are consistent. Otherwise, you may introduce more problems. But yes, it would be ideal to measure it without even sample holder. Not possible though. So, if I have, it's the easiest case. If I have the pure amorphous phase, so that I can do a measurement of my pure amorphous phase. getting the instrument background, and I'm afraid this is hard to see in the back, but maybe you can see here the gray line, which is running here. I hope you can see it, maybe a little bit clearer here. So that's a refined instrument background. And the accuracy should be pretty good because we are not using some empirical profile function here for the peaks of the corundum, but the fundamental parameters approach. So the peak shape is usually if the pattern is well resolved, is better defined than with an empirical profile shape function with many profile parameters. Here, you are refining essentially only one parameter, and that's crystallite size. If you would do this with a Thomson-Cox-Hastings function, you are already talking about 4 to 6 refinable parameters. The effect is a little more correlation, of course, with the background parameters. It might be tiny, but it is an effect which you want to avoid if you can. So this is fundamental parameters, just crystallite size, one peak parameter to define the shape. And if we can assume that the shape is well defined over the whole angular range, then of course we can get a very good estimate of the instrument background here in this case. If we have fluorescence, forget it. It becomes increasingly difficult. But this is copper and corundum. Fluorescence is not an issue here. Also, the standards from this are sufficiently crystalline. So what I refined here as the instrument background is reasonably good. You would use that as a constraint in your subsequent refinements, but constraints have the disadvantage that they are very hard conditions. So what you would do in practice, and I hope I'll be able to show that in a minute, in the software is you would, for example, add another function like a linear a polynomial of first order, which you would add to, for example, the background function, and that would allow it to scale and also to distort the measured instrument background function a little bit. So this is a nifty trick, which is sometimes useful. I show you how this works in a minute. So ideally, I will have two models then. So if I do not have the pure amorphous content with the knowledge of the instrument background and with my mixture pattern here, I can, I can be able to work out the amorphous part of my pattern. The instrument background will run somewhere here, this way. So the difference, ideally the difference between my measured powder pattern and the instrument function represents the amorphous phase, with of course all allowance for error, dependent on how good I can distinguish between the peak intensities and the amorphous phase. And if I have two amorphous phases, it's only getting more difficult. But it can be done, not in all cases, but in a significant number of cases. Yeah, and also, I mean, just for the records, I think it has absolutely no implications on our analysis. No, the amorphous background often, and in this particular case very clearly, contains a Sachs signal. So the difference between here, the increasing instrument background, which is due to the air scattering, and the observed intensity for the amorphous phase here at very low angles is a Sachs signal. And this can also be seen here, maybe again not so easily in the back. This here is now a series of mixtures with various levels of amorphous content. And what you can hopefully see is that in all these refinements, this is a surface refinement, there's one instrument background function used here, the gray line. And of course, the instrument background does not change if the amorphous content changes. So all the intensity which is underneath the measured intensities here for the amorphous content, for the various amorphous content, is a small angle X-ray signal, and that, of course, in size also changes with the concentration of the amorphous phase. So this is not to be confused with air scatter. So that's the point I would like to make. The air scatter part is here. This all is small angle X-ray scattering. Was that somehow clear? I have another exam, but maybe I save this for the end. Let's do some topaz maybe. Do you know how many peaks these are? Three. You spoil my. You spoil my exam. Okay, done. Yeah. So, for those of you who would like to follow now regardless, but you don't have to, when I love to work with cheat files if I make a demo like this, so I have some input files already prepared so that I can return to them quickly if I mess something up. What I would like to show first in this context is, where is it? Determination of the instrument background. So here, this is my corundum pattern. Very low background. Here's 0 counts. Let's have a quick look at how the refinement would look like. I think I can skip most because Robert has shown you the details. So I loaded a data file in XY format. Source emission profile for copper K alpha radiation. I prefer the 5-line model of Hölzer. Instrument, the background function. That's actually the function I would like to refine and to define as my instrument background function later on. Here's the instrument, 173 millimeter radius, detector slit 0.3 millimeters, fixed divergence slit 1 degree, and we have solar slits, I think, of 4.6. Yeah, 4.6, and the secondary side has none. That is therefore a refined solar slit. Corrections, I will only use sample displacement. We could use the 0 error instead, as the angular range is up to 140 degrees. I thought it's actually 160, no, 140. You could, I mean, if it really has to be, you could also refine on 0 point and sample displacements simultaneously, but normally it doesn't make sense. It only adds a redundant parameter. The instrument had a secondary monochromator. That's also why in this particular case, the secondary solar slit did not exist. And I will refine on absorption, can turn it off in the first one because corundum has not a very high absorption. So you have significant penetration of the beam into the sample. This will add some peak asymmetry. And that's all. There's not more to tell. Here is the refinement. And if I believe, and if I believe that these points here are background, then my refined background function will be the instrument background function. That's pretty much it. And nobody could prevent you from now for example, save the background refinement results, which is here in this particular case, it is a Chebyshev polynomial, and use these as they are in all other refinements, which we've done on the same instrument in the same configuration. Same measurement parameters, of course. But specifically, if you change the measurement time, if the intensity is different, of course, the background will be at a different level. But this is what I said earlier. I could now add a second function, which I show you in a second, using the text input window, just a linear function which allows me to scale the background, shift it up and down, and distort it a little bit. So my recommendation, if you have to deal with complex backgrounds, and if this is an issue for you, consider this approach and use such a background function as a constraint. So from here, let me go to the mixture. No. This one here. So this is the mixture. It consists, in this particular case, of two phases. There is the corundum, and there's the silica dust. And let me briefly check that I'm not lying at you. That's what I want. So I have two powder patterns loaded now. There is again my corundum pattern here, and maybe you can read here. I hope you can. I have replaced the refine flag for the Chebyshev polynomials by a name, by a parameter name. And if I'm doing that, this will allow me to do a constraint to other parameters, specifically the background parameter in the second powder pattern here. And if that has the same name, there will be one background function refined on both patterns, right? This will allow me to get the pure amorphous phase without the instrument contribution. So that's the first iteration. And here we go. And the result of this refinement is now a Chebyshev polynomial with the same coefficients for both phases. Can you see that? If I switch between the two entries, the numbers remain perfectly the same as they should. This is also true for this background function here. I'm actually using two background functions. One is the Chebyshev polynomial of fifth order, and the other one is a 1 on x function. And also this 1 of x function has got a name, 1 on x, it is now the same function in both refinements. So this is just for demonstration purposes. What you would do typically is you would, for example, put it could be a macro, but it could go also in a file which is called topaz def, if I remember correctly, where you can enter some defaults. And you could force topaz always to start up with these background function at the beginning. So the key would be if you do not want to do either of these two possibilities, you would note these coefficients and this one on X parameter and simply reuse it from refinement to refinement if you assume that the instrument background has to be the same. With that, you also got the silica intensity distribution right, because the silica intensity contribution is now exactly the intensity here between the measured data and the instrument function, the instrument background function, obviously. So now you have the true intensity contribution of the amorphous phase, and you can try to model it in the next step to use it as an additional phase in quantitative phase analysis. There was a hand?
What wanted to know if it's a peak phase or if it's a HLIS.
Can be both. Yeah, it can be both. Yeah, bitte.
And you compare also the mixture in the same pattern.
Yeah. And I want to show it. I mean, it should be the last step. But yeah, of course, yeah. So the you may have noted that I've been cheating a little bit because I have already used a model to fit to the silica contribution. Now, if you know topaz, then you know that this little icon here means it's an HKLI phase. HKLI phase is the acronym we are using. That's not really an acronym, but it represents either poly refinement or a Lebesgue refinement, depending on what you want to do. Personally, I use only poly refinements because they diverge, they converge much better and faster. The Lebesgue method, however, has the advantage that it has no parameter correlation. So sometimes, if you want to determine a good background function, it would make sense if you do a Lebesgue fit, because intensities are not part of the least squares process, and therefore the intensities will not be correlated with the background parameters. It depends on what you prefer, and it is often also case dependent. In principle, the poly method converges better, is more stable, but it is perfectly fair to use either of them. So if we have a quick look at the silica phase, before I try now to do this from scratch, what I've done here is I am implying that I know the unit cell of the amorphous phase, which is, of course, a little bit problematic because I do not. And if I turn on the tick marks, you can get an idea of what I've done. And this actually brings me back to the question we just heard. Is this a peaks phase or is this an HKLI phase? I can, of course, represent such an instrument as such a intensity distribution with single peaks, with a series of single peaks, keep them fixed and declare them as my refinement model. Also, however, if I'm lazy in particular, I simply have chosen a space group which gives me a series of equally spaced peak positions. The lattice parameters here are, of course, completely arbitrary. They have absolutely no physical meaning, But what it gives me is here simply a series of peaks. And what you see here in the form of the red calculated curve is nothing but a sort of Pauli refinement of my amorphous phase using a series of peak positions which have no physical meaning. A very, very simple and easy way to do that, we could use single line fitting instead. And I'll quickly show you that. I will turn off the peaks phase, the HKL phase here, and we will instead do a single line fit. So, hold on. So maybe I insert a couple of peaks. Where's my ident? Yeah, could be the fundamental parameters function. It doesn't matter. Actually, just put a few peaks in here. Maybe it's like this. It's not looking really good. And I think this is because I forgot to fix the background. I'm sorry. To redo that. And if I feel that my peaks are not giving me the perfect distribution, I mean, here's some misfit here. You can see it in the back in the difference plot. I can add some more. The important point is it does not matter if the peaks have any physical sense. What you want to have is a perfect description of the intensity envelope, because at the end of the day, you are dealing with the envelope and you are scaling the intensity envelope to your observed pattern in the data. The individual peak intensities and positions do not matter. So under the bottom line, what I've got here with a couple of 6 or 7 randomly put peaks is the same intensity distribution which I've done with a fully arbitrary unphysical Pauli fit. Yes, please.
So we cannot use that the amount. Is it good to first like we need to parameterize it, and then we will use the PT amount.
If you want to do this in the context of the Rietveld methodology, then you have to model it. You could scale the observed data. That is the so-called pattern matching approach. The disadvantage of the pattern matching approaches is mostly the fact that you have no handle of preferred orientation, for example. You're really just scaling 2 patterns against each other. You need to have reference measurements of all phases. This was quite successful about 20 years ago, but it is not at all as powerful as by as modeling your contributions. Yeah, please.
If you use a silica powder, this is it reduces the dimensionality of your pipe to obtain the signal. So it is the shorter range, the special and very shorter range. You can use the symmetry of your silica.
Okay, yeah.
Use you put the constraint in a very short distance of your the wings. You can put 10 Armstrong and you obtain the right symmetry.
Yeah, you can do that. I could, in this particular case, also use even the crystal structure of cristobalite to come to pretty much the same result. These are all alternative methods. I believe it is important to be aware that such methods exist, because there's not just one single method which will always give you the best result, particularly if you're dealing with more difficult cases. So yeah, that is all possible. I think maybe the concept to this point of time looks a little bit overwhelming, But if you think about what the Rietveld method, for example, is doing, the Rietveld method is at no point of time trying to decompose or deconvolute peak overlaps. The Rietveld method does not know and does not care about peak overlaps. What the Rietveld method does is it tries to fit to the intensity envelope. And the individual peak intensities, they are attributed by the constrained structure. So if you have no structure, and if you do not need necessarily to have the structure, like in this case here, what counts, what is important for you is some way of describing the envelope. The envelope is what the Rietveld method would calculate from the crystal structure as the calculated data. And where the information comes from at the end of the day, it doesn't matter. It is least squares fitting of a calculated function to an to observed data set, right? Bernd?
I'm always here.
Oh, cool. I wasn't sure. So, relative intensity, peak intensities, peak positions could be saved again as in this case, a peaks phase. The same could be done with the HKL phase. Now, this is a description of the intensity distribution, but we cannot do quantitative phase analysis with this yet. What is missing? Remember what the Rietveld method is using to calculate phase amounts? We have, of course, a scale factor for each phase, and then we have this important group of parameters ZMV. Remember that? Z is the number of formula units, M is the mass of the unit cell, and V is the volume. These parameters are calculated from the known crystal structure. If you don't know the crystal structure, what could you do? You create a mixture with a standard and derive a ZMV because you know the weight percentage of your two phases. So it is what you get then is, of course, the ZMV of the phase, which you use as a standard, for which you know the crystal structure, which serves as a standard, as an internal standard. So for the unknown phase, you can then derive the ZMV, which has no physical meaning again, but it's just a number, and you can use that instead of the Rietveld ZMV, and what you've got then is the so-called Ponck's method. So let me show you this, and I should maybe quickly go back to the presentation of this morning. So this here is the Rietveld, Howard, and Hill extension to do quantitative phase analysis. You have the scale factor for each phase. ZMV is unit cell number of formula units, unit cell mass, unit cell volume. And for a particular phase, you simply do the division through all other scale factors ZMV for all phases present, and this gives you the phase amount. Now, in the Ponck's case, in the amorphous phase case, we do not know what ZMV is. If we, however, rearrange the equation with a known weight for both phases, let's say 50-50, with the ZMV for the standard phase and with the scale factors for the standard phase and the unknown phase, we can derive a empirical ZMV for the unknown phase. And once we have this empirical number for the unknown phase, we can do quantitative phase analysis for amorphous phases, for disordered phases, whatever. And that's actually a very powerful feature with the disadvantage that you have to do this calibration step. So you have to do at least one mixture. Usually this is sufficient. You should also know, however, that this empirical ZMV is only true for a particular wavelength. If you are using a different wavelength in a different instrument, you have to do the exercise again. But otherwise, you can use the ZMV for your non-crystalline phase, put it like this, globally for all other mixtures where the same phase is present. So you can actually build up a database where you have structured data and Ponks information altogether. Just keep in mind that the ZMV calibration factor for Ponks will change if you're using a different wavelength. So that should be, I hope, my last refinement here. So I have the instrument background function. I have an intensity distribution for my amorphous phase. Right, here's still my background. In this case, it's a simultaneous refinement again. And here is my silica. So remember, this is a Pauli or a Lebye refinement. I'm dealing with refinable individual intensities to do a Pauli refinement. So what I need to do is, where's my list of peaks? It is here. Once I've done the refinement of my envelope function, I have to fix all intensities as refined because they represent, obviously, the unknown phase. So just run it again. And here's my background again, taken from the corundum. This is my amorphous phase. This here is my crystalline phase, and let's have a look at the silica details here. What I have got is a cell mass of 0. Of course, there's no crystal structure. Yeah. So this is the parameter now which I have to calculate, and you calculate this using this formula which I've shown you here. I have scale factors for standard and for my unknown phase, for my amorphous phase. So the scale factor here 5.059 whatever. For the silica, here is my corundum scale factor. Where is it? 766 something, right? So this goes in here. This is 50-50%. Okay. The ZMV for the standard is calculated from the crystal structure. It is ZMV, where's my mass? Here, 611. Now I need the appropriate number for the silica by filling in this equation here. I wish I had that in Topaz to do this calculation. Fortunately, I have a pocket calculator, or a mobile that works as well. So once you fill this in, you can do the quantitative refinement, the quantitative analysis. So I want to clear the data and do my last refinement, which is which I think it is. Let me quickly check if the calibration factor is here. Yeah. Ponks. Silica ponks. Yeah, and if you do the maths, what you get is actually this value 3615. It is a totally empirical parameter. It has no physical meaning, but it gives us, or it puts our intensities on an absolute scale so that we can use it in connection with phases for which we have the crystal structure. And if we refine that now, we know the phase, or we know the expected content is 50-50. This is not a terribly difficult pattern, but it demonstrates if your sample behaves well and if your methodology behaves well, quantitative phase analysis can be 1% accurate. In real life, it is not. Remember what André Gignac said. But what you have done here is you have created a phase now for the silica phase. It is accurately corrected for background. The background is, of course, the same for the individually measured phases, the individually measured silica and the corundum. That's the assumption. And this way, you can not only quantify one, you can even quantify 2 or 3 amorphous phases if you can sufficiently discriminate between the individual contributions. Disordered phases, stacking disorder, turbostratic disorder clays. It's a very powerful method, but it is not as convenient as a ritual method. Clearly, you have to put some more thoughts into it. But very powerful, I would say. I think in general, if you have to deal with disordered materials or with amorphous material, the Pong's method is a method of choice. This is what I wanted to show you. You have the step-by-step instructions. You will get another little tutorial file, as I promised to you in the morning, which is only covering this particular example, so you don't have to go through the entire Topaz tutorial manual to find it. Try it out if you want to. I think it is really a lot of fun doing Pongs.